Good morning. In this lecture today, I will solve different problems using force method and stiffness method. For example, assume we have this system. This is our roof system. We have 3 rods. The length of these 3 rods are equal. We attach these rods to one rigid beam. This is rigid beam. So 3 rods, and each one you see both ends, it is hinged, so we will have only one axial force. It will be tension or compression, and the length for each rod is they are equal. Material property for each rod is the same, so Young modulus is E for each one. Cross section for the first rod it is A, for the second rod it is 2A, for the third rod it is 3A. And from here to here the length is L, this is space again it is L, and even this length is L. We have 2 external load. The magnitude of each load is P, for example. Load P, load P. So magnitude of each load is P. The space between these 2 loads is L again. The location of these 2 loads, it is unknown. From point 1 to 3, the location it is unknown X. I don't know where I should put these 2 external loads. The space between these 2 loads it is L, but I don't know the X. X varies from 0 to 2L. Problem statement says find X so that this beam remain horizontal after the load is applied. So we have roof, we are hanging 3 rods. Each rod's length is L. Cross-sectional area for the first one is A, for the second one it is 2A, for the third one it is 3A. The material property is the same, E, these are known value. The space between each rod is L, length is L. This system, we attach these 3 rods to one rigid beam. Initially this rigid beam is horizontal. After applying a load, you know, if we apply load, this will move down and it will rotate because it is not symmetrical system. We want to find X so that after applying these 2 loads, again this beam, rigid beam, remain horizontal. What does that mean? It means the formation in the rod 1, 2, 3 should be equal because initially this rigid beam is horizontal. After applying load, each one will deform. So we have delta 1, we will have delta 2, we will have delta 3, deformation in rod 1, 2, 3. If they are equal, again, this beam will remain horizontal. Where is the location for this set of external load? If you look at this system, if we want to find internal forces in these members, in plane structure, for 2D in plane structure, we can write 3 equilibrium equations. First equilibrium equation is summation of forces in horizontal direction is equal to 0. That will not help us here because we don't have any external force in horizontal direction. Second equilibrium equation tells us we should write summation of forces in vertical direction. If we put summation of forces in vertical direction, For example, if the internal force here, I assume F1, internal force here F2, internal force here is F3. What I will have, summation of forces in vertical direction is equal to 0. It will be F1 plus F2 plus F3 minus P is equal to 0. From here we can write F1 plus F2 plus F3 is equal to 2P. This is my equilibrium equation. Another equilibrium equation, equilibrium of moment. If I write equilibrium of moment, for example, respect to point 1 is equal to 0, I will have F2 times L plus F3 times 2L minus P times X minus P times L plus X is equal to 0. I'm writing summation of moment respect to point 1, F2 times L plus F3 times 2L. Both of them, they want to rotate this rigid beam counterclockwise, so positive, minus P times X minus P times X plus L is equal to 0. From here, we can write F2L plus 2F3L is equal to Px plus P times L plus X. So this is one equilibrium equation. This is second equilibrium equation, and equilibrium of force in horizontal direction here will not help us. But how many unknowns do we have? F1 is unknown, F2 is unknown, F3 is unknown. Everything here is known. This L, E, A, everything is known. The only unknown we have, it is X. We want to find X. But internal forces, in terms of external forces, they are unknown again. So I don't know what is the F1, what is the magnitude of the F2, what is the magnitude of the F3. So I have two equilibrium equations and I have three unknowns here in terms of the force. So I cannot find F1, F2, F3 using this equilibrium equation. This kind of system, later on I will explain, we will call it determinate structure. We have determinate structure, we have indeterminate structure. Determinate structure, this kind of system we will call it indeterminate structure. We have determinate structure, indeterminate structure. Determinate structure, we will call those structure, we can find reactions all internal or internal forces using equilibrium equations. Those kind of structures, we can find reactions or internal forces using equilibrium equations. We will call it determinate structure. If we cannot find internal forces or reactions using equilibrium equations, those kind of structures, we will call it indeterminate structure. Here we cannot find F1, F2, F3 because the number of unknowns are more than number of equilibrium equations. If number of unknowns are more than number of equations, we cannot find those unknowns. So we will call it indeterminate structure. How many unknowns here in terms of force? We have more than equilibrium equation, 1. We have 3 internal force unknown, but we can write 2 equilibrium equation here. So this is indeterminate, and the degree of indeterminacy is 1 degree. So here we will need another equation in order to find F1, F2, F3. That another equation comes from deformation. Here problem statement says find X so that this rigid beam remain horizontal after deformation. That means delta 1 should be equal to delta 2 should be equal to delta 3. So delta 1 is equal to delta 2, that is equal to delta 3. Delta 1, it is F1, internal force in member 1. times the length of member 1, L, over EA. Delta 2 is F2 times the length of member 2, L, over E times 2A. So it will be 2EA is equal to delta 3 is F3 times L, the length of that member, divided by E times A. Here A is 3A, so will be 3EA. This will be third equation. From here, L, they will cancel. EA, they will cancel. From here, I can write F1 is equal to F2 over 2. That is equal to F3 over 3. If I plug this here, what I will have? Instead of F1, I will put F3 over 3. Because F1 is equal to F3 over 3, I will plug here. Plus F2 here is equal to 2 F3 over 3. Instead of F2, I will plug 2 F3 over 3 plus F3 is equal to 2P. From here, I can write 3 F3 plus 2F3 will be 3F3 plus 3F3 will be 6F3. So 6F3 will be equal to 2P. This will be 2F3 is equal to P. So F3 finally will be equal to P. If F3 is equal to P, in that case, F1 will be equal to P over 3, because instead of F3 I can plug P, and F2 will be equal to 2P over 3. Instead of F3 I plug P, it will be F2, 2P over 3. Now I have F1, F2, F3. Once I have F1, F2, F3, if I write summation of moment respect to here, I plug everything here, I can find X. Instead of F2, I can put F2 is equal to 2P over 3 times L plus, instead of F3, I will plug P, 2PL is equal to Px. I plug everything here in this equation, is equal to Px plus PL plus Px. From here, I will have 2Px is equal to, if I take this to other side, this will cancel that. Here we will have only 1PL. And if I add that there, I will have 3, 5PL. P and P, they will cancel each other. So X will be 5L over 6. So X finally will be equal to 5L over 6. So if I put these set of external load in the X is equal 5L over 6 after deformation, this rigid beam will remain horizontal. The way I solve it, you see, first I found internal forces. This method we will call it force method. Let's solve this problem again one more time using stiffness method to see how we will approach using stiffness method. I should remove everything because I need space. Okay, here, if I want to solve using stiffness method, I have again the same rigid beam. Instead of each member, I put one spring with equivalent stiffness. Here, The first one, K1, will be EA over L. K2 will be 2EA over L, and K3 will be 3EA over L. If I call EA over L as a K, this will be 2K, this will be 3K. So the stiffness of this spring I call K, this is 2K, this is 3K. Problem statement says find X so that this rigid beam after deformation remain horizontal. That means deformation for each spring should be equal. So deformation for this spring, if I assume it is delta, this should be delta, this should be delta. So what is the force in this spring? F1 will be K delta, F2 will be 2K delta, F3 will be equal 3K delta. You know, in one spring, stiffness times deformation will give us internal force in that spring. From here, if I write summation of forces in vertical direction, because here we have external load PP, and this is L, and this axis is unknown, we will have F1 plus F2 plus F3 is equal to 2P. That means K delta plus 2K delta plus 3K delta is equal to P. This will be 5K delta, 6K delta is equal to P. From here, K delta will be equal to P over 3. So K delta is equal to P over 3. If I take moment respect to point 1, for example here, to see what we will have the force times distance, so 2K delta times L plus force times distance 3K delta times 2L minus P times X minus P times X plus L plus X is equal to 0. If we add these together, here we will have, this is 6K delta, 2K delta, this will be 8K delta. So this will be 8K delta L let's see, is equal to Px plus PL plus X. What is the K delta? K delta is P over 3. So instead of this, I can plug from here P over 3. I will have 8P over 3L is equal, this term is equal to Px plus P times L plus X. From here, I can write 2Px is equal to, if I take the other side, it will be 3/8PL minus 3PL. So 8PL minus 3PL, it will be 5PL. So instead of this, I can write 5PL. P and P, they will cancel each other, so I can delete from both sides. This 2 comes here, so it will be 6. So X finally will be equal to 5L over 6. And this is what we got from using force method. You see stiffness method and force method. If you understand the concept, it is almost the same. But you will see later on in several examples, sometimes it will be much easier to solve problem using the stiffness method. And sometimes we will prefer to solve using force method. Again, we should practice and learn both methods. Thank you so much for watching this lecture. See you next session.